Now that we've seen how we can take a matrix and use a matrix to summarize the information in a system of linear equations, we can now discuss row operations. So row operations are any one of these three concepts where we can interchange any two rows, we can multiply any row by something that's not zero and replace it with that product, or we can replace a row by the sum of that row and a constant non-zero multiple of some other row. So we can notate that by saying interchange rows 2 and 3 as an example. And you'll notice, say in the next two, our capital letters are the new rows, our lowercase letters are the old rows. So if we take row 2 and multiply it by 1/3, and that would be our new row 2. That would be an example of this second row operation. Or we can take -2 times row 1, add that to row 2, and that would replace R2, row 2. So what are the benefits of these row operations? Row operations yield another matrix whose corresponding system would have the same solutions as the original system of equations. So we're not altering the equation's solutions, or the system of equations solutions. We're just making our system simpler in its matrix form. So here we are given a matrix, and we want to write the corresponding system of equations. So there are two rows, so there will be two equations. The first column will correspond to the coefficients of x, the second column will be the coefficients of y, and then we'll have the right-hand side. So our first equation will be 2x plus 6y equals 44. Our second equation would be 3x plus 1y equals -14. So here is our corresponding system. Now what we're going to do in part B is we are going to replace row 1 with 1/2 of the original row 1. So our new system, our new matrix, notice we're not replacing row 2, so row 2 will stay the same. We'll have 3, 1, -14. But then row 1 is going to change. Row 1 will be 1/2 of the original. So we're going to take 1/2 times 2, 1/2 times 6, 1/2 times 44. So we will have 1, 3, 22. Now in part C, we're going to take -3 times row 1 and add that to row 2, and that will be our new row 2. So notice row 1 isn't changing now. So we have 1, 3, 22 is staying the same. So I'm going to write up here, we're going to take this first row, we're going to multiply by -3, we're going to add it to row 2. So what we obtain is 1 times -3 plus 3, and that yields 0. 3 times -3 plus 1 is going to be -8. 22 times -3 will be -66 plus -14, that will be -80. Now we are going to take row 2, and we are going to multiply it by -1/8. So row 1 will remain the same. But the second row, I'm going to take 0 times -1/8, that's 0. We're going to take -8 times -1/8, that will give us positive 1. Negative 80 times negative 1/8 will be positive 10. Now let's take a look at what we've seen, or what we've obtained up to this point. If we convert this back to our system, we'd have x plus 3y equals 22, and y equals 10. So it would be easy to find out what x is through back substitution. 10 substituted back in for y would be x plus 30 equals 22. X would equal negative 8. So whenever we see our matrix written with ones along a diagonal, or at least with ones with zeros underneath, they may not be in a diagonal, then it's going to be rather easy to go backward and find out what our x's and y's are. And so we call this row echelon form. And so for row echelon form to occur, we need a 1 to be the first non-zero entry in the row. So here we have a 1, and then the first non-zero entry in this row is also a 1. And under each one are zeros. So let's take a look at some examples. These three matrices are in row echelon form. So notice we have 1 is our first non-zero entry, and there are zeros below it. And then in this row, our first non-zero entry is a 1. Now let's look at our second matrix. We have 1s in our first entries in each row, and there are zeros always below each 1. Now above, we don't care. Look at this one. We have 1 is our first non-zero entry, 1 is our first non-zero entry, and then in this row, we have a bunch of zeros, and then we have our 1. Below our 1s, we have zeros.